Hello everyone, in this lecture I'm going to continue chapter 4 and talk about the routing algorithms in chapter 4, which is about network layer protocols. Before I start talking about routing algorithms in the third layer of the network, I'm going to briefly explain and introduce IPv6, which is another version of IPv4 Internet Protocol. The initial motivation of upgrading IPv4 was that the 32-bit address space is too small for many devices that are going to be online and be connected to the internet. Because with 32 bits, we can only have 2 to power 32, which is equal to around 4 billion unique IP addresses, and this is not enough for many the hosts and end systems that are going to be connected to the internet. Also, there are some improvements in IPv4 that they wanted to make in IPv6 to improve the speed of processing and forwarding packets. Also, for facilitating quality of service, some header parts has to be changed in IPv4. That's why they decided to upgrade IPv4 and introduce IPv6. IPv6 datagram has 40-byte header, which is fixed length header, and it's 2 times more than what we suggested for IPv4. We said for IPv4 we assume that the header is 20 bytes, but here we have 40 bytes. And also another difference between IPv6 and IPv4 datagrams is that IPv6 doesn't allow fragmentation. Here you can see the details of IPv4 datagram header. As you see above data, we have the header elements, we have destination address and source address. As I said before, IPv4 has only 32 bits, but now here we have the address of 128 bits, which is 4 times larger than IPv4 and can provide up to 2 to power 96 larger address space than IPv4. So in other words, you can simply say IPv6 address space is too large to be filled out by unique and real IP addresses. In fact, practically you can say we have infinite number of IPv6 addresses, so there's no need to be worry about the address space size and the number of unique IP addresses anymore. Also, an interesting part of the header is the flow label. If you remember, there were no flow label in the IPv4 datagram header, but here in IPv6 we identify the datagrams that are going in the same flow by a flow label. So the concept of flow is not well defined, but you can think of a flow as a set of datagrams that are handled in the same time interval and by the same set of routers. Also, in IPv6, the checksum is removed entirely to reduce the processing time at each hop. And since the header length has to be fixed and 40 bytes, the options are allowed, but outside of header, uh, using the next header field. Also, ICMP-v6 is the new version of ICMP. As I said before, ICMP was the protocol designed for IPv4. Now ICMP-v6 is adaptable to IPv6. The transition from IPv4 to IPv6 is very slow and it cannot happen overnight. It may take many years. So we would have some networks in which some routers run IPv6 while some other routers run IPv4. And in order to handle this situation in which we have a mixture of IPv4 and IPv6 routers, we have to have a concept called tunneling that I discuss in the next slides. In summary, tunneling means the IPv4 datagram carried as payload in IPv4 datagram among IPv4 routers. So if you look at the physical view of this network here, assuming that A, B, E, and F are running IPv6 and only C and D are the ones who run IPv4, routers B and E assume that they are physically adjacent, although they are not, but they assume that there's a tunnel that connects B and E immediately without any other IPv6 routers. So this is the logical view that B and E think they have between them, but the truth is there are two other IPv4 routers between B and E, but we use IPv4 tunneling to connect B and E using IPv6 protocol. The way that we implement the concept of tunneling is that assume that we have a datagram on router B. Obviously, the datagram on router B is an IPv6 datagram. As you see, it has flow numbers, like, they're all the, the source and destination addresses are IPv6. Each address is 128 bits long, and then when we are sending this datagram to router C, you have to wrap it into a IPv4 datagram, which means that the red one is an IPv4 datagram which contains the source and destination IPv4 addresses with where each source and destination has only 32 bits, but the whole IPv6 datagram that came from B becomes becomes the data of the whole IPv4 datagram that you see in red. And then after this red datagram is forwarded by C to D and by D to E. In D, we do an extraction and we remove the red part of this datagram, and then the remaining part becomes the IPv6 datagram, and E can simply forward the blue datagram, which is an IPv6 datagram, to F, because both E and F run IPv6. So by doing this procedure, there's a logical tunnel between B and E, and you can logically you can think that B and E see no routers between them, and they assume that there's an immediate physical connection between B and E, and they are running only IPv6, not IPv4. But in reality, we have a mixture of IPv6 and IPv4s in this network, but IPv4s create an IPv4 tunnel. The IPv6 adoption is so slow that U.S. National Institute standard estimates in 2013 that only 3% of industry IP routers are IPv6, and Only 11% of US government routers run IPv6. The others, they all run IPv4, and there's a long time needed for deployment of IPv6 routers, maybe 20 years or more, because there are many countries that don't even have 15% of IPv6 routers in their network in 2017 or 2018. So there's a long way to go for all the countries in the world to completely switch to IPv6 and remove all our IPv4 routers. Okay, so here we start discussing the routing algorithms in the network layer. As a reminder, you have to know that routing algorithms are different from forwarding tables. Forwarding, the process of forwarding means transferring one datagram from one router to another router by, uh, uh, displacing a datagram by one hop. However, routing means finding the best path for a datagram to reach from one end of the network to the other end system. Obviously, routing algorithms are the ones who fill out the local forwarding tables for each routers. So after routing algorithms fill out the local forwarding table for all of these routers, then the routers can do forwarding, and in a group work, they all can do the process of routing uh, packets and datagrams through the best path possible. When we are talking about routing algorithms, we have to have some graph abstraction of the network because the network is complicated, so we have to remove a lot of details from the network. We consider the routers and end systems to be the nodes of a graph, and the link between routers and end systems to be the physical links between them to be edges of a network. So if you remember from your discrete math class, a graph is a ordered pair of two sets. The first one is called the node set or set of nodes, and the second one is called the set of edges that connect these nodes. In this example, the set of routers are called the set of nodes, and the set of links between routers are the set of edges. However, the way that you see set E looks like, we have ordered pairs. So when we have an ordered pair of U and V, it means that we have a directed edge. So we should have a direction from U to V, or for example, there's a direction from U to X, right? If we want to have a undirected graph, instead of these ordered pairs, we have to have sets. So U and V, if U and V are in this set, or U and X are in a set, or V and X are in a set, then you can say E is the set of edges for a undirected graph. But this graph that you see here with this edge set is not an undirected graph. It's a directed graph because every edge has a direction. Why? Because every edge is represented by an ordered pair. These are ordered pairs, which means the order of elements matters. But in this book, we don't really care a lot about the graph abstraction because this is not a discrete math book. This is a network book. Another notation that you need to remember is that the cost for every link is represented by this symbol C of x and x prime, where x and x prime are two adjacent nodes or two adjacent routers that are connected by a link. So C of x1 x prime shows the cost of the link connecting routers X and X prime. For example, here C of W and Z is 5, which means the link between uh, routers W and router Z has the cost of 5. Cost here is equivalent to the delay. So if the cost is higher, it means that it takes longer for a data or datagram to be transferred over that link. A path is a set of is a sequence of adjacent links. For example, if you have a path from routers x1, x2, x3 all the way to xp, it means that there's a link between x1 and x2, and there's a link between x2 and x3, and there's a link between x3 and x4, all the way to there's a link between x sub p minus 1 and x sub p. Therefore, when you want to find the cost of a path, you have to add the cost of all the links that participate in that path. So in this example, you have to add C of x1 and x2 by C of x2 and x3 by all other costs up to C of x sub p minus 1 and x sub p. So a key question that leads us to creating routing algorithms is what's the least cost path between two given nodes like U and Z. This problem is a classic graph problem that we sometimes call it single source shortest path, which means minimizing the cost of or the length of the path from one single source to all other nodes in a graph. So this problem needs an algorithm that which we call as routing algorithm. There are many algorithms in computer science that are proposed by many computer scientists like Dijkstra. But in this course, we only talk about routing algorithms in the view of a network person. So routing algorithms means an algorithm that finds the least cost path between any two nodes. Some routing algorithms have global information about the network. Sometimes some of them have decentralized information about the network, and the one who have global information, in those algorithms, all routers must have the complete topology of the graph, which means that they must know all the nodes and all the edges of the graph, and they should know how the edges are connecting the nodes for the whole network, and also they need to know the network's link costs. And these algorithms are usually more precise, but they are much more expensive to implement. In this lecture, we talk about linked state as an example of those algorithms with global information. On the other hand, we have decentralized information. There are some algorithms in which routers know only physically connected neighbors and link costs to neighbors, not all the link costs, or not all the nodes, only the neighbors. And in these algorithms, we use an iterative process of computation and exchanging information between neighbors to find a solution for shortest path between two, or least cost path between two nodes, and then this solution eventually converges to the optimal solution that algorithm with global information can obtain. But the good thing about decentralized the algorithms is they are much less costly than the global information routing algorithms. And obviously, if you have a super gigantic network like the internet, having a global information, making routers know all the information about the whole network is practically impossible. Therefore, decentralized algorithms work better for large scale networks. So, among the decentralized algorithms that we have, in this lecture, I'm going to talk about distance vector, which interestingly have the similar idea that linked state has, but the implementation of distance vector is decentralized. However, the implementation of linked state is centralized. Also, there are another classification of routing algorithms based on how often the network topology and the network link cost may change. In some networks, we have a static situation in which routes change slowly over time because the changes on links are very slow, they happen very slow. But we have some dynamic routing algorithms in which the routes change more quickly and they are more responsive to the topology change of the networks. Let's start with the explanation of linked state routing algorithm. Some of you may have been familiar with Dijkstra algorithm. Dijkstra algorithm is a classic solution to the problem of single source shortest path in a network in a general undirected graph with positive weights. In this concept, weights means link costs, and then it's an iterative algorithm. It has k iteration after k iteration. Uh, you know, the the nodes in the graph know their shortest path or the least cost path to the source that is given by the problem. To explain the Dijkstra algorithm, you have to know some notations. For example, C of x and y shows the link cost between node x to node y, and D of v is the current value or the current calculation of cost of path from the source node, which is a specific node, to the destination v. And the P of V is the predecessor node along path from source to V, which means the node that which is visited by the path by the shortest path from source to V right before V. So it's a predecessor node along path from source to V, and M prime is the set of nodes whose least cost paths are definitely known. At the beginning of the algorithm, M prime only contains the source, but as we go over the algorithm and as we do more iteration in the algorithm, the N prime size becomes larger and larger, and it contains more and more nodes in the graph until at the end of the algorithm, M prime contains all the nodes in the graph. So here is the pseudocode for the Dijkstra algorithm. As I said at the beginning, M prime only contains the source, which is U here, and for all other nodes, we have to first initialize their distances to the source U. All nodes that are adjacent to U, which means the neighbors of U, will get the distance equal to the cost of the link that connects U to their neighbors V. And if V is not the neighbor of the source, we have to set the distance of V the distance of u to v to be equal to infinity, which means it's not reachable from u, but this is just the initialization. It doesn't mean that there's no path from u to v. But later, as we go through this loop, the distances becomes less and less until at the end of the algorithm, all of the d of v's show the minimum possible cost of path between u, which is the source, to all other nodes v in the graph. So what does this loop do? In each loop, we first find w, which is the node that is not in set n prime but has the minimum distance from u, and we add that w to n prime, and after we do this, we update all of the distance of dv's for all v's adjacent to w that are not in set n prime. How do we update the distances? The distance of v should be the minimum value of the current distance of v, and the distance of w plus the cost c and the cost of link connecting w and v. So here is a short explanation of this this equation that updates the distance of v from node u. Let's assume that you have this is the source, and then what we want to do is we want to find the shortest path from all the vertices from u, and this is n prime that initially contains all the initially contains only node u, but eventually it will contain all other nodes in the graph. But and assume that w is the node that had the minimum value of d, and it was not in the set of n prime, and we just added w to the set n prime in line 10 of the algorithm. What does this equation in the line 12 means? It means that in order to find the minimum distance of the node u to node v, we have to find the minimum value between two possible paths. U is v is reachable from u in this path, which means a direct path, not a direct path, a path from u to v, and a path that goes through w. The path that goes through w has the cost of d of w plus c of v and w. This is c of v and w, this is d of w. If you add these two values, we'll get the cost of this path that I mentioned here. So you have to get the minimum of that value and the value that we have already calculated for the distance between u and v, which is the current value of d of v. So the current value of d of v and then the value of d of w plus c of w and v are two candidates for the new value of d of v. Whichever are smaller becomes the new value for d of v, which specifies the new minimum distance from u to v. And then you have to continue this loop until all nodes become part of n prime, and that time you can just make sure that all the d of v's are the best and minimum values of cost for path between the source u and that node v. Here's an example of running the Dijkstra algorithm. As you see, we have 5 different steps. In the first step, we assume that only u, which is the source, is in the set n prime, and as we go further, we add w in the first step, x in the second step, v in the third step, y in the fourth step, and finally we add z in the last step. And after adding z, all nodes of the graph become part of the set n prime, and that's when we finish the Dijkstra algorithm. So what does this the table says? In each row we summarize the result of each iteration. So the first row summarizes the result of the first iteration, in which in the first row is the initialization step. So as you see, the distance of y and z are set to infinity because they are not adjacent neighbors of they are not neighbors of u, so they are not adjacent nodes of the source. That's why the distance is infinity. For all others like x, w, and v, since they are adjacent to u, what we need to write for the distance is their immediate link cost. So the distance between u and x would be 5 because of this cost that we have on this link. Or the distance between u and w is 3, and u and v is 7. And then after the first step, after step 0, we have to do the first step, which means we have to choose the node with the least distance. So as you see here, we have 7, 3, 5, infinity, infinity. The minimum value between these numbers is 3, so we have to choose w to be added to n prime in the first step. And then after adding w, we have to run we have to use the equation in line 12 of the previous algorithm to update the distances between u and the other nodes. As you see, the updated distance of v becomes 6, so it becomes less than 7. And the distance between the u and x remains the same. It would be still 5. The distance between u and y becomes 11, which is much smaller than infinity. And then as we continue, more updates will happen, and at the end, in the last step, there is no update in the cost. And as you see, the least cost path from u to v has cost 6. The least cost the path to w has cost 3, and the least cost path to x has cost 5. The distance between u and y is 10. The distance between u and z is 12. And these numbers are the minimum possible values. You cannot find any the shorter path. And then as you see, we have two values for each element of the table. One is 6, the other is w. W is the predecessor. Using predecessors, we can reconstruct the shortest path. So this table not only gives you the shortest path, but also it gives you the actual path. If you follow the predecessors, you should be able to reconstruct the path. As you see here, if you want to reach from u to z, you have to follow this path. So how can I find out this path using this table and using predecessors? You have to first find the predecessor of z. As you see here, the predecessor of z is y. So the node before z is y, and the node before y is v, because v is the predecessor of y, so you have to use v to reach y, and then you have to use w, as you see here, to reach v, and you have to use here. You have to use u to reach w because predecessor of w is u. So this table is enough for you to find out all the shortest path from u to all other vertices. If you draw all the shortest path, you get a shortest path tree here in this in this graph. The edges that are specified by red color are the ones that are participating in the shortest path tree. The other edges don't participate in the shortest path tree for the source u. Here you can see another example of the Dijkstra algorithm. And then after running the Dijkstra algorithm and constructing the shortest path tree from U, you can simply fill out the forwarding table in U, saying that if you want to go to the V, the best link is to choose this link. If you want to go to other destination X, Y, W, or Z, you have to use this interface, the interface to reach to X. The complexity of the extra algorithm, if you have n nodes, would be n squared. But if you do a very a smart implementation, and if you use complex data structures like Fibonacci heap, then the order of the algorithm becomes n log n. And the extra algorithm is interesting because if the link costs change by the traffic flow, then there would be a possibility that the route that the extra algorithm suggests oscillates the datagrams between different points of the network and between different routers. So there are many interesting the observations that you can see in the book and in this slide, that how the extra algorithm can respond to change. But we are not gonna go over it in detail because we are going to talk about how distance vector is the best fit for responding to changes in network topology and also link cost change in networks. At this point in this chapter, we talk about distance vectors algorithms. The distance vector algorithm is based on an equation called Bellman-Ford equation, which is very similar to the idea that we saw in Dijkstra's algorithm. It basically says the distance from x to y, which is represented by d sub x in parentheses y, is equal to the minimum of distance from v to y and the cost of reaching from x to v, where v is this where v can be every neighbor of x that is adjacent to x. So if you want to schematically draw x, v, and y, let's assume that here we have x, this is x, and this is y, and we have a bunch of neighbors for B, and then these neighbors are immediately connected to X with some links, and obviously the cost of each of these links are represented by C of X and V. So this is V1, so this is C of X and V1, this is V2, this is V3, V4, and maybe all the way to V sub n. And then each of these V's are connected to Y by some path. So there's a distance between each of these neighbors of X to Y. So the distance between these neighbors to Y is represented by D sub Vi. In this example, in the first one, D sub V1 in parentheses Y, right? and for the second link would be d of v2 of y, d of v3 of y, d of v4 of y, all the way to d of vn of y. So how many possible paths do we have from x to y? One is through the top link, the top path. The other is through the second top path, which goes through V2. The other is to go through V3. The other is to go through V4, and all the way the other is to go through Vn. So if you get the minimum of all of these costs, you get the best path from x to y, right? So it's a very logical equation. This is called Bellman-Ford equation, and that's, it's very similar to what we have in the 12th line of Dijkstra algorithm pseudocode. So here's an example of Bellman-Ford equation. So in order to find the shortest path from node U to node Z, it uses the minimum equation that we saw in the previous slide to find the smallest or the shortest path between node Z and the neighbors of U. As you see, the neighbors of U are V, and W. So this is for V, this is for X, this is for W, and then the distances of Z from the neighbors of U should be added by the cost of the link that connects the neighbors to U, and then after that you have to get a minimum between these three values. And after that, at the end, the cost would be equal to 4, which is true, and shows the shortest path between U and Z. As you see, this is the shortest path between U and Z. 1 plus 1 plus 1 plus 1 plus 2 is equal to 4. The distance vector uses the same idea for creating a decentralized algorithm that each router in the graph in the network runs, and they create some distance vectors which are in the following form. Every router like X maintains the distance vector of itself from all other nodes in the graph, and then it shares its distance vector with its neighbors, and also it stores the neighbors' distance vectors, and this way it can run the Bellman-Ford equation to update its own distance vectors based on the neighbor's distance vector. And also, if something changes in the network, for example, the cost of a link is changed, is different in a network from time to time, then distance vectors of neighbors or distance vector of a router will change, and that router with different distance vector is responsible to advertise this change to the whole to all of its neighbors, and this way everyone can have the updated information. Here you can see the details of the distance vector algorithm and the idea that is the Bellman-Ford equation, and how one router sends or advertises its distance vector to its neighbors if some change happens in the network and some link cost changes, and when such change happens and a router sends its new distance vector to the neighbors, all the neighbors are responsible to run this Bellman-Ford equation on their local computer to find out the new distance vector of themselves. And if their own distance vector is different from gets updated, they have to also advertise the change in their own distance vectors to all other neighbors they have. In summary, we can say distance vector algorithm is an iterative asynchronous algorithm because each local iteration caused by a local link cost change and DV or distance vector update message is uh, sent from the local node to the neighbors. So everything is asynchronous and there is no coordination between nodes. And then it is distributed because each node runs the same uh, piece of pseudocode and notifies neighbors when its distance vector changes. And here is the summarization of what distance vector algorithm look like. At each node, a node waits for a change in local link cost or a message from neighbor. The message obviously contains the distance vector of the neighbor, and that can trigger the recomputation process so that it can re-estimate all the distances from all other nodes to itself, and then if the distance vector to any distance to any destination has changed, it notifies all neighbors so that the news of changing its distance vector can be advertised throughout the network. Here's an example of a very simple example of distance vector algorithm. Uh, the first one is the set of all distance vectors that node X stores. Obviously, the first one is the distance vector of itself, which shows the distance from node X to other nodes X, Y, and Z. The second table shows the initial information that node Y has. It only knows its own distance vector, but it doesn't know the distance vector of the neighbors. So it assume that they are all infinity, and same for node Z. This is the table that node Z stores. But after the first message exchange, for example, if you look at the node X table, you see that the information that nodes Y and Z had uh, will be stored at node X, and based on the Bellman-Ford equation, the distance vector of node X itself changes, and that make node X to advertise its new distance vector to their neighbors, which are Y and Z. Here you see the process of advertising new distance vector to the neighbors Y and Z. The same process will happen for Y. The Y gets the distance vector from neighbors X and Z gets the distance vectors of X and Y and stores it in its own table, and also at the same time it uses the Bellman-Ford equation to update its own distance vector. As you see, the distance vector of Z changes after it receives information from the neighbors X and Y, and then it has to notify other neighbors of Z with this change, so that since everyone notifies each other of the change, at the end, at the last step of this algorithm, as you see, all of these three tables contain the same distances, because all the tables will converge to each other eventually because of the message exchange between neighbors. So in this part of the lecture, we talk about two scenarios in which a link cost changes, and we talk about how distance vector reacts to this link cost change. In the first scenario, we assume that the cost of a link will decreases from 4 to 1, for example. As we see in this figure, the link between x and y has distance had cost 4 initially, and then it is now equal to 1, and this link cost change will propagate through the network very fast using the distance vector algorithm. Why? Because if node y detects such link cost change, it updates its own distance vector and informs the neighbors, and after some point z receives the update from y and updates its own table, computes the new list cost to x, and sends its own updated distance vector to the neighbors. And again, y receives the new z's distance vector, and y looks at the cost and see that there's no change, so y doesn't send a message back to z because its own distance vector doesn't change. So after one or two iterations, the link cost change will affect on the distance vectors, and the distance vectors will will get updated successfully after a few iterations of distance vector message exchange process. So it's not a big deal. The link cost change travels very fast in this case, but later we see that some other link cost may change. Some other list cost changes may cause problem for distance vector algorithm. In this case, we have the same topology, but the cost of link between x and y increases from 4 to 60. So we have a bad news here. The bad news in distance vector travels slow, despite what we saw about the good news, which travels very fast in the network, but bad news travels super slow. I don't want to explain this problem in detail, but this problem is called Poisson reverse. I will post some extra slides that can explain this problem in detail, but in summary, you can think of this problem as a very slow adaptation of distance vector to a link cost change. When the cost will increases substantially in a link like this in a network, and it takes the distance vector algorithm 44 iterations before the algorithm stabilizes and no more messages get exchanged. So if you compare it to the other slides link cost change, you see that the other one, on the other one we had only 2 iterations before the algorithm stabilizes. Here we have 44. So as you see, the bad news travels slower than the good news in distance vector. Here you can see the comparison between linked state and distance vector algorithms. Among all of these differences, the most important comparison is the speed of convergence. The LS has an ON squared algorithm, which requires n times e messages, where n is the number of nodes and e is the number of links. And we may have oscillations if the link cost changes, but the distance vector has a very variant convergence time. It all depends on how the link costs change, but we may have the count to infinity problem or the problem that we just see in the previous slide, in which it takes the distance vector along a large number of iterations before it gets stabilized. Finally, we talk about broadcasting and multicasting and how broadcast and multicast routing take place in the network layer. There are two different implementation of broadcasting. One is to duplicate message in the source, and the other is to duplicate message whenever it's necessary. If you duplicate message in the source, for example, here we have to send it to three different uh, outlets. So we duplicate message at the source into three different copies, and then send the copies throughout the network. The network becomes super crowded because of unnecessary traffic that we created by duplication at the source. But if we duplicate whenever it is necessary, for example, we don't duplicate at the source, but when it reaches to R2, then R2 duplicate messages into two copies and send each copy to the routers R3 and R4. This would be a better and a smarter duplication, and would use resources, network resources in a smarter way, and will cause less flooding in the network. We have three different solutions for in-network duplication. One is called flooding, the other is called control flooding, the last one is a spanning tree. In flooding, every node that receives a broadcast packet sends a copy of that message to all neighbors, including the neighbor that it receives the packet from. And the problem is that we create cycles and we create a broadcast storm, so it's super inefficient and it's not practical, so flooding is out of question. The other solution is to use control flooding. Control flooding is a little bit smarter because a node only broadcasts packet if it hasn't broadcast same packet before, which means that it doesn't broadcast the same packet twice. That will remove all the cycles. However, it is not the smartest solution. The smartest solution is to use the spanning tree and only sends packets if they are very, very necessary. So this way we don't have redundant packets received by any node. I'm going to show you what a spanning tree means in the next slides, but in summary, a spanning tree is a subgraph of a graph that is cyclic, and it is connected, and it contains or spans over all the nodes in the graph. Here is an example of a spanning tree. If this is the original graph, the broadcast should happen on a spanning tree that looks like the one that you see in the right. In the spanning tree, only the links that I specify with red are participating. The other edges, like these two, are not, and this one are not part of the spanning tree. So if you use this spanning tree to do the broadcasting, that would be the smartest broadcast, because we would have no redundant packet forwarding. Here at the beginning, assuming that D initiates the broadcasting, D forwards a copy of message to G, a copy of message to E, and a copy, not E, sorry, only sends a copy of message to G and B, right? So since D is the source, we first send a copy to G and send another copy to B. Why doesn't D send the copy to E? Because the edge between D and E doesn't belong to the spanning tree. And then B forwards the message on the same path that on the same on all the links that participate in the spanning tree, and also A forward the packet to C because the link A to C is the only uh, link participating in a spanning tree, and then C duplicates the message and sends one copy to E, the other copy to F. So as you see here, we only have 6 packet forwarding, and we don't have any flooding or controlled flooding, and everything is very, very efficient because we don't have redundant packet forwarding. There are many ways to create spanning trees. There are some algorithms like Prime and Kruskal. Here in the book, it mentions one of the many ways that the spanning tree can be created.